All right, welcome back, everyone. We're going to carry on now. We're going to talk a little bit about some of the activities of ASSA. We've got Tim Cooper speaking with us, who I mentioned already. He's the director of the Comet Asteroid and Meteor section of ASSA. And he's going to be talking about some of his adventures looking for asteroids in the Kalahari. Great, thank you, Tim.
Thank you, Daniel. Good morning, everybody. Title of my talk this morning then is From Vesta to the Kalahari on the trail of the Motopi Pan Meteorite. And I'd like to explain a little bit more about the process that we followed to analyze video footage of the very bright fireball that came into the atmosphere as a result of the entry of asteroid 2018 LA that happened on the 2nd of June 2018. And as a result of the analysis that we did, we were able to locate the full site of the meteorite, and we then subsequently mounted an expedition where we found 23 fragments. So our story starts on asteroid Vesta around about 22.8 million years ago with an impact which formed the crater Rubria. You can see it in the left-hand panel towards the right-hand side. Rubria is a small crater, diameter about 10.3 kilometers, which is situated in the troughs of the Divalia Fossae region on Vesta, which is ejecta from the impact of previous impact, which caused the Ria Silvia Basin. So subsequently, after that fragment was ejected from Vesta, it traveled in space for about 22 million years. It was then first detected in space by the Catalina Sky Survey early on the morning of the 2nd of June 2018. So the discovery images are on the left-hand side there. And then after that, there were several other telescopes which managed to secure images, which enabled astronomers to calculate a fairly accurate orbit for the object. So the initial data that came in of this object was an absolute magnitude of 31.1, given an albedo of 0.25. That gave a diameter for this rock about 156 centimeters, spinning around about once every 4 minutes. And it was traveling as it came into our atmosphere at around about 17 kilometers per second. So based on the astrometric observations of this object, that enabled astronomers like Bill Gray and others to determine a path across the Earth's surface. And so you can see here the path across Asia in the early afternoon. It was then predicted to come towards over Africa, north of South Africa, across Botswana, and then into Namibia. And the prediction at that stage was that there was an 83% chance of an impact with Earth's surface somewhere over Namibia. The actual position which we determined from the work that we did is actually shown by the red cross that you can see here just over Botswana. So the first indications that we had that something had happened was that there were, during the early evening of the 2nd of June, a few reports were made to the ASSA sightings page of a very bright fireball. At that stage, we didn't take anything too seriously, but immediately afterwards, this video was posted online by a gentleman called Byron Swanepoel. He's a farmer in the Ottosdal region of the northwest of South Africa, and he made the claim that a meteorite had fallen near to, or he actually made the claim that a meteorite had fallen on his farm, and other eyewitnesses said that it had fallen near to the town of Deelpan. So just to give you some idea of where that is, so Pretoria, Johannesburg is over here. Ottosdal is in this location here. They made the claim that the meteorite had fallen around about Deelpan, which is a distance of 68 kilometers And our work showed that it actually fell here in Botswana, which is a distance of 10 times even further away. This is one of the common misconceptions with very bright objects like this, is that people think that it fell over the nearby hill. So while we did not believe that any meteorite had fallen near Dielpan, the question was, where did the meteorite fall, if one did fall at all? And so what we had to do was then to locate videos of the object and calibrate those videos then in order to determine the fall site. And we managed to find 6 videos. This involved a 4,500 trip by car, looking at various sites where people had found videos, and we found 6 which were usable. We found 3 videos which actually caught the actual passage of the fireball. The one here from Ottosdal, from Gaborone, and also from Kuruman in South Africa. And then we found 3 videos which also captured shadows of the bright flash from the disruption of the meteorite from the asteroid. First of all, here in Khansi, here in Mau, and here in Reikops in Botswana. So what we needed to do is we needed to calibrate very accurately these videos in order to determine the altitude and the azimuth of the various events in the path. So this is the video that Barent Swanepoel posted. It's 2 screen grabs from his video showing the asteroid as it comes into the atmosphere towards the upper right of the frame, and then the moment at which the very bright disruption occurred is here. And so what I needed to do was to now calibrate this, and I needed to do this by placing my camera in front of the camera which took this view here in such a way as there was no distortion and the aspects were absolutely aligned. So this is the calibration image that I took. I went back to the site of this. Unfortunately, the video camera that took this scene was under the eaves of a 2-story building. So I had to climb up on a very high ladder and try to place my camera right in front of the video camera, and succeeded in doing that. And this is the calibration image that I took, and you can see that there are some bright stars. So because there are some bright stars in the image, and we know exactly what the positions of those stars are accurately at the time we take the image, we can then use that as a calibration image to then determine the various events on the path of the fireball. So that's the calibration image. I then went back to my home, and I took the frame grabs from the video, superimposed these on top of the calibration images, and measured the positions of these stars very accurately. So here you've got Alpha Geminorum, you've got stars in Lynx and in Ursa Major. We determined the position of these stars very accurately, and because we now had those positions, and because everything now here is nicely aligned, we can determine various positions of the fireball and its path, including the very bright disruption. You can see here also that this disruption, as seen from Ottosdal, is pretty much on the horizon. So, and that's the reason why this farmer believed that the meteorite had actually fallen on his farm. So unfortunately, I can't show the actual video. This video went viral. It showed in the first day over 1.5 million hits. The rights to it were subsequently brought by a third party, and so in respect of that, I can't show you that video. What we then did is I then traveled into Botswana. I found video taken with a commercial property in Gaborone. This is a screen grab from that video. And then this is the actual video. So hopefully this will now process, and you will see when the timestamp above is around about 15 seconds that the fireball will enter at the top, and you will see the moment of the bright disruption. Okay, so that was how the fireball appeared. So the job was now basically to understand the position of exactly where that disruption occurred. So once again, several days after the fireball, I returned to the scene of this plant. Fortunately, the owners agreed to put the lights off for me, so you don't have these foreground lights around the actual plant here. And that enabled me then to capture this image. And once again, we can see we've captured a number of stars in Geminorum and in Ursa Major, because we know the positions of these lights, of these stars. We can then determine the positions along the path of the fireball. So that's a superimposition of one screen grab on top of that calibration image. I did this for several images to give several positions, then also the direction at which the disruption occurred. So that gave us a second chord on top of the Otto's Dal. After stopping in Gaborone, I then proceeded up the western side of Botswana, stopping at an engine garage. I asked the garage owner if I could have a look at their security cameras. He obliged, and we managed to find this particular video. So this is a screen grab from his video. It did not capture the actual bowlight itself, but we could see the fireball as it was reflected and moved from right to left along the top of this vehicle. And then at the moment of the bright disruption, you can see that there is a pole here which cast a shadow onto the forecourt. So armed with this image, we then drew a line across that shadow there, because you can see that there's a very nice pattern of the tiles. We were able to recreate that line quite accurately, then placed a camera on that line and imaged then in the direction of the pole which cast the shadow, capturing stars. And because the position of those stars were known, we could very accurately determine the direction of this shadow, which is then in the anti-direction of the actual bright flash. At the same time, I was going up the western side. My two colleagues, NASA's Peter Jenniskens and Okavango Research Institute's Oliver Moses, managed to find two more videos which cast shadows. First of all, this is a shadow of a tree which is cast onto a roof at a hotel in Maun. And then secondly, this is inside a fast food restaurant which has captured a pole which is outside, and because of the shadow of this pole, and you can see that here you have the pattern from the tiles in the restaurant, we were able to understand exactly what the direction of that was, took calibration images again, and that gave us the direction of the bright disruption from Raycops. So that gave us 5 chords. We processed then the latitudes, longitudes, and altitudes of the different cameras, the actual time, the azimuth, and the elevations that we determined from the astrometry. And that gave us a very good solution, which meant that we did not have to go and calibrate the 6th one, which would have been in Kuruman. We were happy with the 5 that we had. And once again, if you look at the Otto's Dal, you can see that the elevation of that disruption is around about 0.1 degrees above the horizon. So it's pretty much on the horizon. So giving us those 5 vectors, that gave us a full site for the meteorites in the northern part of the Central Kalahari Game Reserve, which is this blue shaded area here. It's a very large game reserve in Botswana, home to the Big Five. And here you can see the cores that we had from Ottosdal, from Gaborone, from Khansi, from Mount, and from Rakops. So that's the very approximate position of the strewn field. But if we look at this in much greater detail, the solution that we got from our astrometry is the red ellipse. The blue line here is the actual orbital solution for the asteroid from the astrometry from the professional telescopes. And the black ellipse here is the position in that orbit for when the asteroid would have been at an altitude of 27.8 kilometers, which is the altitude at which it exploded. So now that we had that very accurate position for the location of the strewn field, we mounted an expedition, and like any country in Southern Africa, unfortunately, any meteorites which fall are properties of the state. So we needed to get permits. The second point was that it fell in a very remote location in the central Kalahari Game Reserve. So we also needed to have some rangers with us. So we managed to arrange that through Mohotsua Gabadiwe. He is in the center here from the Botswana Geophysics Institute. He headed up our team. They've got NASA's Peter Jenniskens on the right-hand side here. On the left-hand side is myself, Oliver Moses from the Okavango Research Institute, our two guides here, and then a representative from the Botswana National Museum. So that became our search party. We were now going to look for meteorites from this object. As I mentioned, it was in a very remote area, several kilometers from the nearest road. There was literally nothing there, so we had to take everything in, including all of the water that we needed for drinking and cooking. There was no washing, of course. So that's our base camp, which was very close to the strewn field that we located. This is us actually searching for meteorites, so it gives you some idea of the terrain that we had to search. Basically grassland with small shrubs. And what we did then was to spread out on a fence with around about 10 to 20 meters between us, looking left and right as we move forward. And from that basis, we then on the ground which didn't belong there. So once again, this is a close-up of the area that we searched. Once again, you see the ellipse here. This is the path of the meteorite. The black line that you see here is our solution for the strewn field location after we applied the effect of winds at different altitudes. So that meant that this is the area which we actually wanted to search. You can see here that the asteroid was moving in this direction. So any large particles actually after the disruption were carried forward. Any small particles were actually blown backwards in the path. So we expected to find in this direction smaller and smaller pieces, but more of them. If we move in this direction, we expected to find larger pieces, but much fewer. So the first expedition that went up a couple of days after the asteroid came into the atmosphere, they concentrated on this area here, looking for large pieces, which was not our strategy. We wanted to go for the smaller parts, smaller particles, and this orange areas are the areas that we searched based on the Garmin GPS that we used to record our path. And each one of these yellow dots is actually the find location of a fragment from that meteorite. So you can see here that the particles are in the region of around about 10 grams down to about 1 gram, exactly as we expected to find. So this is just a gallery of the fragments that we did find. You can see that many of them have this very bright black fusion crust. It they looked almost shiny, as though they were wet. They weren't wet, of course, they were completely dry, but they had this very, very shiny, high gloss appearance that they appeared to be wet. So that simplified looking for some of these particles, because there were many other things there which were not meteorites, but they looked like meteorites. Things like Gemsbok droppings and things like that. There were pieces of charcoal from a recent grass fire, and we needed to be very careful to make sure that we didn't, in looking for objects that we needed to pick up as meteorites. So there are a few objects here which you can see are clearly different. So this is a very fragmented object, and you can see the achondritic appearance of that particular interior. There's another one here. This is the fragment that I found. You can see that there are some flow lines on that. So based on the diverse nature of these, we believe that they came from different parts, some from the outside of the meteorite, some from the inside, and the ones which have got an asterisk here, they were sent to NASA's laboratories in the US, and they were destructively analyzed to understand exactly what the meteorite was. It comes back that it was a HED, howardite eucrite diogenite, which is typical of the type of meteorite that you get from the asteroid Vesta. So that's just a summary of the 23 fragments that we found. Again, with the asterisk, these are the ones that were analyzed destructively. So each meteorite recorded with latitude, longitude, and altitude of the finder's name, the date and time that it was found, the affiliation, and the mass of the particles. So you can see the very first one found was around about 18 grams. Most of them you can see are in the region of between 1 and 10 grams. But subsequently to this, there was an expedition which was put up again by Boost in Botswana. They went back to the site several months later, and they found one more fragment with a mass of 92 grams. And I think that will probably end up in the Botswana National Museum. So the evidence for Rubria crater as a source, so the petrography and mineralogy is that of a howardite eucrite diogenite meteorites, which have their origin on asteroid Vesta. The reflectance spectra of the meteorites we found are very similar to other HEDs, also associated with an origin of Vesta. The semi-major axis and the inclination of the orbit are consistent with the region from the inner main belt where Vesta and its vestoids are found. And then the cosmic ray exposure age matches the crater aging models on Vesta and confirmed that the origin is from Rubria crater, which was formed 22.8 million years ago. So that explains the methodology that we used to look for meteorites from this particular fireball. Of course, it was a very valuable exercise in how to locate strewn fields of meteorites. The same technology or same methodologies can be used for other meteorites or other fireballs which are seen in South Africa. We have had recently a number of bright fireballs, some of which may have dropped meteorites, but unfortunately we just were not able to obtain the necessary videos that would enable us then to calibrate and then determine what those locations would be. So there are, for example, the events of June 2017 and most recently in August 2021. These were very, very bright fireballs which were seen to explode, and they were both associated with sounds like thunder. There's no doubt that they would have probably dropped meteorites, but unfortunately we just couldn't get enough video evidence to enable us then to mount a search for those objects. So in conclusion, the bright bolide of 2nd June 2018 from asteroid 20 LA was well seen. It was picked up on several videos. Calibration of those video images enabled us to determine a location for the strewn field for possible meteorites. That included direct images of the bolide and also shadows. Both of those are equally of use. A search for the strewn field then enabled us to find 23 fragments, which were traced back to a particular crater on Vesta. There have been several recent bowlines in South Africa, some which may have dropped meteorites, but in all cases, we've not been able to obtain enough video evidence to enable us to do so. And an opportunity really exists for us to take this methodology and just create the awareness that when there are very bright fireballs, if we can calibrate these images, there is a potential for us to discover more meteorites which have fallen on the southern African continent. So with that, I thank you, and thank you very much for the opportunity to present the work that we did on this particular event.
Thank you, Tim. That was super cool, and congratulations on the successful find. Was the photo of the lion on your search?
Sorry, I missed that.
Was the photo of the lion from your search? It wasn't.
No, it wasn't, but I don't think it was, but there were lions there, of course. That's the reason why we had to have the ranger. And although we didn't encounter any wild animals while we were actually searching, on the way back on the second night, we came across 2 lions in our path, very close to our camp where we were camped. And the following morning, there was a dead giraffe very close by. So we think that they had more interest in giraffe than they did in us.
Cool. Are there any questions from the room here? Otherwise, we'll move on. Thank you again, Tim. Much appreciated.